Recitation 13 about a summation notation, arithmetic or geometric series. All right. Let's see the first one. And we want to write out the following sum. So this summation sign says the index, which is use n. Sometimes we use I, we use j, we use k. So that means the index goes from 1 up to 4. So that means we have the first term, second term, third term, and fourth term. So 1, 2, 3, 4. 4 terms. And each term we add them. So that is what this is summation sign means. Well, 4 terms we add them. So each term we just substitute. So this one, the first one will be A1, right? If we think this as a sequence, right? Let's see. If we think this whole thing as AN, and N start with 1, so this will be A1. This will be A2, and A3, A4. And also one way to think about sequence is you can think about sequence as a function takes natural numbers as input only. So in this case, this equals the AN. All right, but N only, and in this case, the natural numbers, counting numbers. Natural numbers also called counting numbers. You count things like 1, 2, 3, 4, so on and so forth. All right, so you could think that way. So in that case, you just evaluate A1, which is substitute N into 1. So let's calculate here. A1 equals to -1 raised by 1 plus 1, which is 2. Then 1 times 4 is 4. 4 plus 1 is 5. Then divided by 3 raised by 1, just 3. -1 squared passed to 1. So we get 5 over 3. Okay. So the first term is 5 over 3. The second term, A2, which means N equals 2. So I have -1 raised by 2 plus 1, which is 3. And 2 times 4 is 8. 8 plus 1, 9. Divided by 3 raised by 2, which is 3 squared. Well, -1 raised by cube by odd number, that's negative. Then numerator will have 9. Denominator will have 9. So get -1. So the second term, A2, is -1. Then A3. -1 raised by 3 plus 1, 4. Right, 3 times 4, 12. 12 plus 1, 13. All divided by 3 raised by 3. -1 raised by even number become positive. So numerator will have 1 times 13, which is 13. 3 raised by 3, 27. So the third term is 13 over 27. Let's see, the last term in this case is A4. We have -1 raised by 4 plus 1, 5. 4 times 4, 16. 16 plus 1, 17. Then 3 raised by 4. -1 raised by 5, odd number, so negative 17 over 3 raised by 4, 81. So that's plus -17 over 81. Do we have to simplify this, calculate this? No, right? Because this is saying just write out the following sum. So this is good enough. Okay, so let's erase this and keep moving. Let's see 2. We want to write the following sum in sigma notation. So basically it's the reverse of question 1. Question 1, we're given a sigma notation and we want to write out the sums each term. But this one, we have sums. We have 1, 4, 7, means we don't really know how many in between 7 and 298. So the last one is 298. Well, let's observe this sequence. So 1 to 4, that's being added 3. 4 to 7, that's being added 3. Means the pattern continues. So which this we are having our arithmetic sequence. So arithmetic sequence, we have common difference D. So in this case, it's a positive 3 because each time we just add 3. We just add 3, right? If we're treating 1 as A1, let's call the first term A1, right? So A1 equals 1 plus this is common difference 3 times 0. So when we write the sigma notation, maybe we want to start n with 0. So in our sigma notation, we want to write n starting from 0, right? And then the inside we can write as the first term multiplied by 3 times n. Right, let's check A2. So A2 equals 1 plus 3 times 1. 3 times 1. So that's 4. Okay, so this works. Or if you're saying, I don't want n start with 0, I want n start with 1. That's fine also. We just have to adjust this, right? So basically 1 plus 3n is nth term in this case. 1 plus 3n. If we want n start from 0. Or if you want n start with 1, so how do we do this? So A1, we know A1 equals 1. So plus common difference is 3. But because we start from 1, so we want n minus 1. Right? Because when A1 n is 1. 1 minus 1 is 0. So we still get 1. So then we change. So if we want n start with 1, we see n equals to 1. Then the inside an will be 1 plus 3 times n minus 1. Simplify this, we get 1 plus 3n minus 3, which is 3n minus 2, right? So we can write as 3n minus 2. Okay, you see these two are different, right? But this is together because we define n start from 1. And this, if you want to write this way, that's fine also. But this one is start from 0, 1 plus 3n. Okay, now, what's the upper limit? So we need to find out the upper limit. The upper limit, we're going to find out by this one. So we want to find out this is, so n equals to what for this one? So plug in, if we want to use n start from 0, we use this an, right? In our case, we want to figure out n for 298. So 298 equals 1 plus 3n. Subtract 1 on both sides, we have 288 equals 3n. Then 288 divided by 3. 9. 3 times 9, 27. 28 minus 27 is 118, so 96. Right, n equals 96 if we use this one. So we can change this one to be 96. And then we finished. Okay, if you want n start from 0, we say n has to be greater than or equal to 0. Then we have summation sign, n equals 0 up to 96. Then a n term is 1 plus 3n. Right. If we want to start from 1, we say, okay, 298. Oh, hold on, I made a mistake. So this becomes 297 because I minus 1 here, right? Not 2, I'm not minus 10. That's 297. 297. So 3 times 9, 27. 9 minus 7, 2, 27, 99. So this should be 99. I made a mistake. Okay. Not 96, 99. So this, so if n start from 1, we have 298 equals to 3n minus 2. Then we add 2 on both sides, we get 300 equals to 3n. Then n equals to 100, right? So change this question mark into 100. So if n start from 1, then the upper limit is 100. So 3n minus 2. All right, so both answers, either one is okay. Now let's see B. B, we see every term has a factor of 5. So maybe we'll factor out 5. Now, factor out 5, of 2 squared plus 2 cubed plus 2 to the 4th power plus plus 2 to the 17th power. Well, obviously, this is a geometric series sequence, right? Because 2 to the square to 2 to the third multiplied by 2. 2 to the third, 2 to the 4th multiplied by 2. So each step be multiplied by 2. So the common ratio for this geometric sequence is 2. Remember, we have a formula to find the sum of those, right? The sum equals to the first term. The first term in this case is 5. Maybe we can put a 5. Just leave 5 for now. We're just calculating this geometric sequence first, right? So the first term will be 2 raised by 2, which is 4, multiplied by 1 minus, the ratio is 2, r raised by n, 2 raised by n, divided by 1 minus 2, 1 minus r, right? Remember the first term, a1, times 1 minus 2 raised by n, divided by 1 minus r raised by n, whatever the ratio is, divided by 1 minus r. But in our case, the common ratio is 2. So I have 2 squared, which is 4 times 1 minus 2 to the n, divided by 1 minus 2. Okay, let's simplify those two first. 2 squared is 4. 1 minus 2 is -1. So we'll get a -4. Times 1 minus 2 to the nth power. Right? We change this a little bit. Multiply -1 to inside. Have 4 times 2 to the nth power minus 1. Now, so we need to find the n. Right? We need to find this n here. How do we find this n? By the last term, right? By the last term, we need to figure out the nth term. So we see the pattern. So a1 equals to 5 times 2 squared. And our common ratio is 2. So we can rewrite this as 5 times 2 raised by 1 plus 1. And this one comes from here. So this tells us that we can write an, the general term, as 5 times 2 raised by n plus 1. So let's check the second term. The second term will be 5 times 2, 2 squared, right? 2 plus 1, n plus 1, right? A2. A2 will be 2 raised by 2 plus 1, 2/3. Okay. Again, you can start with 0, n, if you want the n start with 0. So here, I want the n start with 1. If you want the n start from 0, you would do n plus 2. Okay, n plus 2. But let's start n with 1. So I get the general term an equals to 5 times 2 raised by n plus 1. Okay, now I have 5 times 2 to the 17th. Let me use this space. I have 5 times 2 to the 17th power. That equals to 5 times 2 to the n plus 1. Oops, n plus 1 power. So I divide by 5 to simplify those. I get 2 to the 17. equals to 2 to the n plus 1. Well, n plus 1 equals 17, right? Because the base are the same. So 17 equals to n plus 1. So that means n equals to 16. Now we'll come back here to find the sum. So I have 4 times 2 to the 16 minus 1. All right. So if you have a calculator, you can calculate the 2 to the 16th power, then minus 1, then multiply by 4. Okay, but I'm going to finish here. Okay, let's see C. Okay, let's see C. C, we have 4 terms. We have 4 terms. We can write this as, oh, hold on. Let's go back. Let's go. Okay, so let's redo this. Let's redo this B. Let me rewrite those two. Oh, okay. So this actually give us K start from 1. So let's rewrite this. So this one, if K start with 1, we have calculated, right? The upper limit will be 100. Then this one will be 3 and minus 2. And this one will be n. If we want to n start from 1, remember this ends at 16, right? And then 16. Then we have 5 times, because we are not finding the sum. Write the following sum in sigma notation. We want to write in sigma notation. 5 times 2 raised by n plus 1. And if you want this 5, you can write it outside, right? If you say, okay, because 5 is a common factor of every term, I can write this way too. N equals 1. Then upper limit is 16. 2 raised by n plus 1. Okay. Or another way of writing this is, because 2 to the n plus 1 is 2 to the n times 2. You can also write it as this. Oh, you know, this we use k. Let's change this to be k. Any variable will do it. K. So k start from 1, finish at the 16, then just 2 raised by k's power. Either form is okay. So this one, you write inside the summation sign 5 times, 2 raised by k plus 1. This one, you factor out 5. Then inside, you have 2 raised by k plus 1. Or you even factor out, for the 2 to the k plus 1 is a 2 to the k's power multiplied by 2. You can even factor out 2. You see, okay, 5 times 2 is 10. Then inside you have 2 raised by k. Okay, either one is fine. Okay, now let's see C. C, obviously, we only have 4 terms. So K start from 1, finish at a 4. Observe the denominator. We have 1 to 3, 3 to 4, 5 to 7. Arithmetic sequence, right? Because K start from 1, so the 1, how do we get a 1? We can do 2 and 2 times 1 minus 1. So that means that n's power, that only the denominator, all right, will be 2 and minus 1, right? The second term, the 3, so how do we get 3? 3 is 2 times 2 minus 1. 5, 2 times 3 minus 1. 7, 2 times 4 minus 1. Okay, so the denominator will have 2k minus 1. I usually like to use n, but here we want to use k. All right, so that's for the denominator. Now for the numerator. The numerator will have x raised by 1, x raised by 3, x raised by 5. You see this 3. So this is 1, 3, 5, 7 is the same as the denominator, right? So I have x raised by 2k minus 1. Now we have positive, negative, positive, negative, so alternates. So we have a -1 raised by, the first one is positive, so we can do k plus 1, right? Because 1 plus 1 is 2. So -1 raised by 2 give us the first term is positive. And that's it. So this is summation sign, right? So the index start from 1, finish at 4. It's alternating sequence. So we have -1 raised by k plus 1 because the first term is positive. When k is 1, 1 plus 1 is 2. Then x raised by 2k minus 1 divided by the denominator is 2k minus 1. All right, that's C. Okay, I want to find, let's see, 3A. We want to find the sum of first 21 terms of this sequence. Well, let's figure out this sequence. Two famous sequence we know is a geometric sequence and a arithmetic sequence. So 5 to 9, that's plus 4. 9 to 13, that's plus 4. 13 to 17, that's plus 4. Okay, arithmetic sequence. So the common difference is 4. So we want to find 21 terms. So the first term is 5. And we need to figure out last term. Remember, for arithmetic, how do we find the sum? It's n divided by 2. Let's see, Sn, right? Sum of n terms equals to n divided by 2 multiplied by a1 plus an. Let's see, so a1 is 5, a2 is 9, a3 so on and so forth, and we want to find a21. So how do we find a21? Let's write it out in general form. So the first one is 5, and the common difference is 4. It's 1 plus 4n, right? Because n start from 1. The first term 5 will be a1. a1 equals 1 plus 4 times 1, which is 5. This is general term. So now a21 equals 1 plus 4 times 21. 4 times 21, 84. 84 plus 1, 85. Okay, now we can plug into this. So S21 equals to 21 divided by 2 times a1 is 5 plus a21 is 85. Well, 5 plus 85 is 90. 90 divided by 2, 45, right? So multiply 21 with 45. 21 we can split into 20 plus 1, and times 45. 20 plus 45, 900. And plus 45, so that's 945. And of course, you can use calculator. Right, so the sum of the first 21 terms as 21 equals 945 for this term. So you don't need to memorize this. You just think about this. Let's read out the term. So the last term is 85. The 21st term is 85, right? And this term will be 81. 81, so this would be 77, right? What's 5 plus 85? 90. What's 9 plus 81? 90. 13 plus 77, 90. Because if you pair up like this from the front and the end, pair them up, the sum will be always the same. But how many pairs we have? We have n divided by 2 of many. All right, let's see B. The sum of first 15 terms of such sequence, alternating sequence. right? So 7 to -14, -14 to 28, 28 to -56, -50. Okay, so each time we see what multiply by negative number, negative what? -2, right? -2 times 7, -14. -2 times -14, positive 28. -2 times 28, -56. -56 times -2, 112. All right, so this is geometric sequence. And R common ratio equals to -2. So in arithmetic, we call common difference. In geometric, we call common ratio. So the sum we have, let's see, S, and in this case, we have S15. So S15 equals to the first term multiplied by 1 minus -2 raised by 15 divided by 1 minus -2. Right? Remember the formula is A1 times 1 minus common ratio R raised by N divided by 1 minus common ratio R. So we just calculate. The first term is 15. Okay, the first term, no, the first term is 7. We want to find out the 15 terms. So the first term is 7. 7 times 1 minus, well, -2 raised by R number is negative. So become 1 plus 2 raised by 15. Then divided by 1 minus negative becomes 1 plus 2, 3. Again, you can plug into a calculator to find out the sum. Okay, but I'm going to finish here. So what is the beauty of this one comparing to arithmetic? In geometric sequence, we don't need, as long as we need how many terms, we know this n, we don't need to find an, right? We only need a1, the first term. And then we need an n, of course, we need a common ratio. But in arithmetic, we need to find an, all right? Okay, so let's see. I think those are the last two questions. Okay, so what does this notation mean? This permutation notation. So permutation, if you have n, k, that's n factorial divided by k factorial and divided by n minus k factorial. Permutation. What does it mean? So this means, think about you have A apples, right? You want to pick 3 out of these 8 apples. How many ways allow you to do that? Right, that's one example. Another example is, let's say you have 3 people in a group, and you have 8 people in a group. You want to pick up 3 to do something. And how many ways of doing that? So we have a factorial divided by 3 factorial. In this case, a is n, 3 is k. And a minus 3, which is 5 factorial. And what's the definition of factorial? That means the counting number and a multiply. The product of counting number is smaller than a, right? So a times 7 times 6 times 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1. Then we see this cancelled, right? Then 2 times 3 is 6, cancel this. So I'm left with 8 times 7, 56. So how many ways? Pick 3 apples out of 8. There are 56 ways doing that. But what if we have a big number? Let's say if we have 80 apples, we want to pick 30. So if we do this, that's gonna be long writing, and we don't want to do that. So how do we do it? So a factorial equals to a multiplied by 7 factorial equals to a times 7 times 6 factorial, so on and so forth, right? Times 6 times 5 factorial. So in this case, we want to write a factorial just like that, a times 7 times 6 times 5 factorial, because the denominator will have 5 factorial. Then 3 factorial, 5 factorial. 5 factorial divided by 5 factorial becomes 1. So 3 factorial is 3 times 2. Then these two cancel. So we get 56. So this is normally, how we calculate the factorial. So we don't want to do, multiply until 1. All right. Well, let's see this one. We have a factorial divided by 4 factorial. A minus 4 is still 4. Right? So a factorial, we can write as a times 7 times 6 times 5 times 4 factorial. Then the first 4 factorial is 4 times 3 times 2. We don't need to multiply by 1, right? Because 1 doesn't contribute anything in multiplication. Then 4 factorial divided by 4 factorial becomes 1. Now we have 2 times 4, which is 8. Simplify with this. Then 3 goes into 6 twice. So we're left with 7 times 2 times 5. 2 times 5, 10. So we have 70. So out of 8, we want to pick 4. There's 70 ways of doing that. Lastly, we want to prove this identity. Okay, factorial identity. This means out of n, pick a k, then multiply by k is the same as out of n minus 1, pick a k minus 1, multiply by n. No, we just use the definition, right? So the first one, so the left-hand side is a k times n factorial divided by k factorial, then k n minus k factorial, right, by definition. So that's the left-hand side. K times n factorial divided by k factorial divided by n minus k factorial. Well, let's see the right-hand side. Right-hand side, we have n times n minus 1 factorial divided by k minus 1 factorial. Then divided by n minus 1 minus k minus 1 factorial. N minus 1 minus k minus 1 become plus 1. So these two canceled. So this one becomes n minus k factorial, right? So we have n minus 1 factorial, but we have this n, right? So n times n minus 1 factorial. That's n factorial, right? Just like a 7 factorial times 8, that's a factorial. So n is a number 1 bigger than n minus 1. So n times n minus 1 factorial, that is n factorial. And the denominator we're left with k minus 1 factorial and n minus k factorial. We have k minus 1 factorial and n minus k factorial. Well, let's compare these two, right? So here we have n factorial, and here we have n factorial. So the numerator are the same. And the denominator will have n minus k factorial. Denominator will have n minus k factorial. But this right-hand side will have k minus 1 factorial. The left-hand side will have k factorial in the denominator. But we have this k multiplied, right? We have a k multiplied by n factorial divided by k factorial divided by n minus k factorial. Well, this k factorial in the denominator, but this k is a numerator, right? So you see k divided by k factorial. Let's think about number. Think about a divided by a factorial. What is that? That's a divided by a times 7 factorial. A divided by a becomes 1. So that's 1 over 7 factorial. So that means k divided by k minus 1. No, k divided by k factorial equals to the k divided by k times k minus 1 factorial. K divided by k becomes 1. So k divided by k factorial, that becomes k minus 1 factorial. Now the left-hand side and the right-hand side are exactly the same. Okay, now we can put an equal sign in between. Okay, that's proof